Cool. Okay. Yeah. So thanks very much, Chris. As you said, covering chapter 17, object orientation. And initially, it looks like there's not a huge amount of content here with only 3 subheadings, but there's quite a lot of depth in these topics. So the book covers what it defines the characteristics of OO languages, which we'll get into in a little bit. It moves on then to discussing trait objects, which are sort of the nuts and bolts of actually implementing polymorphism with Rust. And then we ended up with a nice use case of using an OO design pattern with Rust. So just very briefly, a quick history of OO. So object orientation is a way of modeling programs. The concepts of objects were first used in the Simula language in the 1960s. And these influenced Alan Kay's programming architecture in which objects pass messages to one another. He coined the term OO programming in 1967 to describe this architecture. Yeah, we don't really get to cover history much in this group, although if you did want to check out last week's talk, Richard Shepherd talking about implementing the Enigma machine, I do recommend you check it out if you like software history. It's very interesting. Yeah, so the Rust book says that there's no consensus in the programming community about what features a language must have to be considered object-oriented. I think that's a bit harsh personally. I think there is some consensus because there's lots of shared characteristics between people's definitions. And indeed, you can see that in the fact that many OO languages actually share quite a lot of characteristics. But the book goes on to just run through what it feels are the 4 sort of most high level, most important characteristics of OO and just briefly discusses their level of support for them. So their first characteristics, objects contain data and behavior. I've just decided to take the quote straight from the book because I think it sums it up perfectly. Object-oriented programs are made up of objects. An object packages both data and procedures to operate on that data. And procedures are typically called methods or operations. I don't think there's anything wildly controversial there. Rust clearly supports this form of modeling. Structured enums can hold data, and implementation blocks provide methods that operate on that data. Encapsulation that hides implementation details. So implementation details of an object aren't accessible to code using that object, and that the only way to interact with an object is via its public API. So it's just straightforward, really. So making sure that you talk about, or when you write code, you're talking about the actual operations you want to do, not about specifically manipulating bits of data. It's an abstraction technique to prevent data and information leakage across other areas of the system. In theory, it should mean that your code ends up being more descriptive. I don't think any of the OO disillusionists, I think is the word I'm going to use, here today. So I'm talking about this all in terms of theory. So this is not opinionated. I know maybe some people who are going to go and watch this video again will have strong feelings, because when reading up on this topic, I found a lot of people have strong feelings about OO. Yeah, so as I said, it's an abstraction to prevent data and information leakage. Enables the programmer to change and refactor an object's internals, its behavior, without needing to change code elsewhere. Any code that uses the object should just say, hey, you still do this bit of behavior, but behind the scenes, we can change what that means. And in Rust, encapsulation is controlled using the pub keyword, short for public. Pub determines which modules, types, functions, methods, members are public, and everything else is just private by default. So here's the big ticket item for Rust and OO discussion is inheritance. So we've probably all used it. It's a mechanism where an object can inherit from another object's definition, thus gaining the parent object's data and behavior without having to redefine it. If a language must have inheritance to be an OO language, then Rust is not one. That's lifted straight from the book as well. There's no way to define a struct that inherits another parent struct and auto inherit its fields and method implementations. if you're used to having inheritance in your programming toolbox, there are ways to get around this with Rust or to have something similar. It depends why you're reaching for inheritance in the first place. And the book goes on to elaborate on this and discuss that you probably want inheritance for one of two major reasons. At least this is their reasoning. So first is code reuse. Pretty straightforward. We basically just covered it. If you inherit if one object inherits from another, you can access the methods that are already defined there. You don't have to write it out again. And you can do this in Rust by using default trait method implementations instead. At that point, I got a little bit unclear as to as to how this wasn't inheritance. I think there's probably some distinction there that I'm missing, but you can do it. And oh, that's not come out as well as I hope. Yeah, so here's just an example. We saw this in chapter 10, having a default implementation for the summarize method in the summary trait back in chapter 10. Any type implementing the summary traits would have the summarize method available with this default implementation here, but they can overwrite it if they so wish, which we do here. So the second reason you might reach for inheritance is to utilize it as a type system. So this is basically polymorphism, which we touched on earlier. It's allowing a child type to be used in place of a parent type. It means you can substitute multiple objects for each other at runtime if they share certain characteristics. So to many people, polymorphism is synonymous with inheritance, but that's not actually the case. It's more of a general concept that refers to code that can work with data of multiple types. When you're using inheritance, those types are generally subclasses, but this does also apply to pure interfaces and their use with other types as well. Rust doesn't use the term interface anywhere in its language, but with traits, you can implement something that works a bit like an interface. Sorry, my notes just decided to shoot around. Yeah, so Rust uses generics to abstract over different possible types, and it uses trait bounds to impose constraints on those types. This is sometimes called bounded parametric polymorphism. And again, we saw this in chapter 10. So in that code snippet here, we can see if we've got a function accepting a generic of type T, and it must implement the summary trait. It strikes me as being very similar to C++20's concepts, although I haven't got a lot of experience with concepts in C++. So if anyone has got more experience or knows of any reason why I'm right or wrong, I'd love to know. So why no inheritance in Rust? So what was the design decision behind that? So again, this is the author's opinion now shining through. This subsection of my talk is pretty much reflecting their opinions. So inheritance has recently fallen out of favor. I put that in quote marks because I feel like for the last 5-6 years, I've not met anyone who really likes it. But it is mainly for the following reasons. So there's a belief that it often risks sharing more code than necessary. Subclasses shouldn't always share all of the characteristics of their parent class, but will do so with inheritance. It's possible to call methods on subclasses that don't make sense or can cause errors because the methods don't apply to that subclass. Again, some languages only allow a subclass to inherit from one class, which restricts the flexibility of a program's design. These are kind of big indications that OO probably isn't the way you want to model your system if these OO language features are restricting you from representing your program the way you want. And personally, for my own code, I actually like restricting inheritance. I think it's a good thing for OO, but that's a personal thing that I can move on to another time if anyone's interested. Yes, I've spoken about. Yeah, I know. Again, I know I said before that recently. It doesn't feel that recent to me. I've had the phrase favor composition over inheritance sort of ingrained into my psyche for years now, ever since university. So I don't think this is anything new. But hey ho, for all these reasons, Rust decides to take a different approach and uses trait objects instead of inheritance. So how trait objects can enable polymorphism in Rust. So we kind of touched on this a bit in chapter 8. So we looked at an example where we wanted to use a vector that stored elements of different types, despite the fact that vectors can only store one type. And we got around that, if you'll remember, by having an enum that had variants that held integers, float, text, and basic types like that. And when we know all of our types at compile time, this is a perfectly good solution to use. But the situation we're interested in now is when those types aren't known at compile time. So the example that the book uses is that we want to develop a GUI library that defines a number of items that all have a method called draw. And we want the library to allow users to extend the library with their own types that can implement the same draw. And then we want some extra functionality in the library that could take all those types, the ones it defined and the ones the users defined, and call draw on all of them at the same time. So with an OO language, we might do this by just defining an abstract class or an interface. Might be named something like component. That's the name the book offers. And that would have a method called draw in it, and other classes would inherit from it, and thus inherit draw. Rust doesn't have inheritance, so we need another way to do that. So to implement the behavior we want our GUI to have, we'll define a trait named draw that has one method called draw. And then we can define a vector that just is of type trait object. So a trait object points to both an instance of the type, of a type implementing our specified trait, as well as a table that looks at those trait methods behind the scenes at runtime. We create a trait object by specifying some sort of pointer, such as a reference or a box pointing to some type. And then we use the dyne keyword, short for dynamic. I don't know if there's a better way to pronounce that truncated version of the word. But then we specify the relevant trait. So in chapter 19, we'll cover why a trait object must be a pointer in a bit more depth. So trait objects can be used instead of a generic or concrete type. And whenever we use a trait object, Rust type system will ensure at compile time that any value used in the context, in that context, will implement the trait object's trait. So consequently, we don't need to know all of the possible types at compile time. Yeah, so this is just continuing on with the code example from above. So if I just go back. Yeah, so we're defining our trait, we're defining our vector of dynamic draws, and we want to be able to just go through our list of components, regardless of what type they are. So it's important to note that this is different from defining a struct that uses a generic type parameter with trait bounds. The book provides the example on screen to remind us that a generic type parameter can only be substituted for one concrete type at a time, unlike trait objects, which can be multiple types. And those types can be filled in for the trait object at runtime. If you'll know that you'll only ever have collections of a single type, then generics and trait bounds is preferable to using trait objects. That's because the definitions will be monomorphized at compile time to use concrete types, which we're going to touch on monomorphization. I always butcher the pronunciation. Monomorphization. Got it. We're going to touch on that later in the chapter. But you can see here, so we've got our example with our generic and our constraint. But of course, if we use this, we can only use one type here. So carrying on with the book's example, we've got a toy example, which we have our library provides a button, which implements the draw trait. What the draw actually does for button doesn't really matter. What variables it have doesn't really matter. And if this looks familiar, it should, because it's in chapter 10. So yeah, and we've got another object here, which is called select box. And again, in the example, we're just carrying on with it. This select box we're imagining has been developed by a user. So they want to use the same trait. So pull in draw from our GUI library, and they implement it and they add some code. Good. There we go. So once we've done that, our library's user can now write a small little main function that creates an instance of the screen type, which owns a vector of draw trait object, sorry. And it can assign both the library defined box type and the user's own select box type and call their draw functions. It looks like it's cut off a bit there, but it hasn't actually cut off anything important. So we've got our vector here with a box around select box, which is the user defined type. And we also have a box around button, which is the library defined type. And once that's set up, passed into screen, we trigger screen run, which is just to run through all of the components and call draw. So just to reiterate, when we wrote this library in our example, we didn't know that someone would come along and create the select box type, but screen was able to operate on that type anyway and draw it because select box implements the draw trait, which means it draws, which must mean it implements the draw method. The concept of being concerned only with the messages that a value responds with or responds to rather than the value's concrete type is similar to duck typing in other languages. If it walks like a duck and quacks like a duck, it's a duck. But what's different here is that we've got the power of Rust type system, which allows us to say, hey, you've definitely got this method because you're sort of fulfilling this contract when you pick up this trait. This trait object means you've fulfilled this contract, so you can call these methods. Yeah, and so the book just gives us a quick example of a situation where it won't compile. So we try to pass in a string and we'll get some error messages where it's quite helpful and tells us that it needs to be of type dynamic draw. Trait draw is not implemented for string. Easy peasy. Yeah, I was struggling to work out which bullet points to best put on this slide, and clearly didn't update the slide. So if you remember, I mentioned monomorphization earlier, which was also covered in chapter 10 when discussing trait-bound generics. So when the compiler generates non-generic implementations of functions and methods for each concrete type, sorry, let me start that again. The compiler generates non-generic implementations of functions and methods for each concrete types that we use in place of the generic type parameter. And the code that results from this is doing static dispatch, which is when the compiler knows what method you're going to be calling at compile time. This is opposed to dynamic dispatch, which is when the compiler can't tell at compile time which method you're calling. Straightforward, right? And in these cases, the compiler emits codes that at runtime will tell Rust to, hey, go and figure out what function to call. When we use trait objects, Rust must use dynamic dispatch because it can't know all possible types at compile time that could be used to implement this trait. So instead, it relies on pointers stored in the trait object to tell it where to call at runtime. So we introduce a bit of a trade-off here where we've introduced a little bit of overhead into finding where that method is at runtime, but it has increased our code flexibility. So swings and roundabouts. So yeah, I just want to talk about this next idea is the concept of object safety for trait objects. So trait objects must be object safe. It's what the Rust language defines as object safe, which we'll get to in a minute. It's enforced because once you've used a trait object, Rust no longer knows the concrete type that's implementing the trait. So the book alludes to quite a few complex rules that govern what makes it object safe. But it basically just comes down to tool rules. Make sure that the return type on its methods isn't safe, as is in itself, straightforward. If it doesn't know what type it is, it can't resolve the alias. And make sure there are no generic types. So it's the same story. If it can't resolve the concrete type, then, sorry, if it can't resolve the generic type into a concrete type, then you can't use it compile time. So it's not object safe. Yeah, and so again, the book gives us another example. So the clone trait returns self, so it is not considered an object safe trait. So when we try to use it as a trait object, the compiler gives us all kinds of warnings, and I really wish that this text was bigger. It was bigger when I practiced before. But it says clone cannot be made into an object. And it even mentions that the trait is not object safe in the error message. Okay, so the final section of this chapter is actually a case study of going through a scenario where we want to implement the state pattern. I think a lot of the benefit is gained from this section is from going through it yourself. So I do encourage everyone to have a go. Don't just rely on watching this, but I will run through it now. So the crux of the pattern is that an object has some internal state, which is represented by a set of state objects, and the object's behavior changes based on its internal state. The idea being that when business rules change, that we'll only need to update the code inside one or maybe more of these state objects. We might have to add or remove some or alter the way they interact, but ultimately nothing using the object will have to see any changes. So the example that we're going to use is a blog post program. And the workflow that we're looking to implement is on screen now. So we want users to create a blog post, and that starts as an empty draft. When the draft's done, we want to request a review of the post. When it's been approved, it gets published. And only published blog posts can actually share content. So if you query another post for some content, it doesn't give you anything. You can't have unapproved posts accidentally publishing their content. Yeah. So here's some example usage of the API for our post object. So you can imagine it's internally utilizing these state objects on each method call. So just thinking about that workflow we mentioned on the previous slide, we want to create a new draft post. We want to be able to add text to it, but crucially, it's still a draft, so we can't publish any content. We want to be able to request a review. Again, we still can't publish any content. Finally, we approve a post, we can publish content. And notice that even though we've discussed, or we discussed before the idea that each method is this post object transitioning between different states, you can't actually see any of that state information at this level. So the idea is that it's all been abstracted away. It's all hidden behind that API. And we've encapsulated it. So to start, creating a post object, it's just an object that owns some content in a string, and it's got some reference to its state. State is a trait object because it could be in any one of 3 states during runtime. We make the state trait private because we don't want to expose it to users of the library. And note that the state is optional. We'll get to that in a minute. So when we create this post object, we set the state value to a draft, which I'm going to cover on the next slide. but it's going to be in the draft state. And this ensures that whenever a new post object is created, it's always starting in the correct initial state. There's no way to create a post object in any other state. Was that? Sorry. Oh, it's supposed to be on this slide. It's cut it off. Bear with me 1 sec. That's actually quite an important piece. Sorry.
One downside to markdown slides is that,
yeah,
when the content doesn't fit, you get absolutely no feedback.
Oh no, I'm going to have to. I don't want to go through the whole process of exporting it again. I'm trying to think what's the best way to do this. Perhaps I should open up a notepad. Definitely shouldn't be sharing these things. We'll cut that out in the recording. Sorry, apologies. Just trying to see if there's a way to increase the font size. Actually, is that
plus?
Plus. Ah, thank you. Is that okay for everyone? Cool. Yes, so we've created a post object, and we've got our state, which is a dynamic state. It's a trait object. We've defined our state trait here, and we've got an empty struct for it and empty implementation for that. And we ensure that whenever we create our first post, or when we create our post object, it can only ever be in the draft state initially. All turned around now. Yeah, and we've got a add text method, which just allows us to append some text onto our content string. It's pretty straightforward. Doesn't do anything with the internal state, doesn't need to do any other checks. So it's just a straightforward append. So next, we want to add functionality to request a review of a post, which should change its state from draft to pending review. So we've done a few things in this example, which I'm just going to double check hasn't also been. This is what happens when you rush. Right, apologies, everyone. So this time round, we've added a public method called request review to post. We've added a public method called request review to the state trait as well, which allows us to call it, which only allows us to call it if we're calling it from a boxed type, which is signified by this syntax here. We've also implemented the function for the draft struct, and we've created a new struct called pending review, which also implements the state trait, and that also implements request review. For the two states, the request review method differs in behavior. Draft returns a new pending review state, and pending review just returns self. So when we call request review on the post object, we can say, hey, get my current state, and we call the take method to take some value out of that state field, leave none in its place, because Rust doesn't let us have unpopulated fields and structs. This lets us move the state value out of post rather than borrowing it. Then we'll set the post state value to the result of this operation. I've skipped out a sentence in my notes, that's why. So sorry, I'll just rewind a bit. When we call request review on post, it calls the state's request review right here, and assigns the result to its internal state member, which would Yeah, and in order to consume that old state, the method needs to take ownership of that state value, and that's why the state is optional. Yeah, so we call take, which gets the sum out of that state field and leaves none in its place, because otherwise we'd have an unpopulated field in the struct, which we can't have, which is how we can move it out of post rather than borrowing it. Oh, for goodness sake. What not to do in a presentation. Right. So the approve method is similar to request review in that it calls a method on the internal state and it uses it to update its internal state. So this time we'll add a new method to the state trait, which is called approve. And we'll also add another new state called published. So here we go. We've got published. It implements request review and does nothing. We've also got approve, which does nothing except return self. It can also only be called on a boxed version of itself because that's defined in the actual state. Trait. Oh, trait and state rhymes. But you can see we've also added approve to pending review. So similar to the last example where draft was the only one that could return a new type from the request review method, approve within pending review returns published. And this is implementing that in the same sort of behavior as we had before, will allow us to transition from request review to the published state. And so finally, we want to be able to return some content. We actually want to do the publishing once we got our published, once we're actually in our published state. So as the goal is to keep all of the rules inside the structs that implement state, we're going to require a new method for the state object. So we've called it content. It's going to take in the post object as an argument, which you can see where we passed in self here. And we're going to get the content string from that. So state has this content method, pass in self. Internally, that queries. I'm just trying to find, is it the next slide? Yes, it did. So, so this is how that content method would actually look like as implemented. So you can see we've got a default implementation on our trait called state for content, accepts a post with these lifetime parameter arguments so that we know how long this post is going to be alive for, because we intend to return its content. And for the published state, that is the only state that will actually implement a version that returns the content, or rather, it borrows the content. So the book's shown us that Rust is capable of implementing OO design patterns, or at least it's told us we can do the state pattern. And if we were to create an alternative implementation without this pattern, we might have used match expressions on each of the post methods, but then that would have meant we'd have to look in several places to understand the full implications of a post being in a particular state. This could get worse as the number of states increases. But with that in mind, the state pattern does bring us the following benefits. The implementation was easy. That's the Rust book's term, easy. I do think it was easy, but maybe I'm just being colored by all the things that went wrong in the presentation. But it is straightforward to extend. It's clearly quite straightforward to maintain, but it's not all perfect. It does have some downsides. So some of these states are tightly coupled together. We rely on explicit transitioning from one to another. So If you wanted to introduce a new state that is in the middle of the workflow or change the workflow entirely, you still have to know how they all tie together. There's still quite a bit of work to do. We've also duplicated quite a lot of logic. Request, review, and approve can't have default implementations because they return self, but effectively they work the same way. And if they did return self, it would violate the object safety requirement of trait objects. In short, following this pattern exactly as defined for OO languages means we can't take full advantage of Rust's strengths. I've just realized we're running low on time. I'll try and hurry up a bit. So it proposes some ways to make it rustic. In the Discord chat, somebody proposed that making code more Rust-like is corroding, i.e. to develop Rust. I think rustic is pretty good. So it proposes two solutions or two ways to make this code more rustic. The first is to encode states and behavior as types. And the second is to implement transitions as transformations into different types, i.e. to leverage the type system. And of course, it's making me do this. So we still enable the creation of new posts with the new function, but now we return a different type called draft post. And this is the only type that has a method available, allowing us to add text. But the draft post type cannot return content at all. It's now impossible for a draft post to be accidentally queried for content because the compiler will not allow it. There's no content method. We've used the type system to enforce that rule for us. I'm not even sure why I'm bothering with these slides now. So we want to enforce the rule that a draft post has to be reviewed and approved before it's published. So a draft post can have its request review method return a type pending review post. This new type only has the ability to be approved. The approved method will return a type post. See here. And that type post is the only one that can have its contents viewed, which we saw on the previous slide or notepad instance. So these types take ownership of self and consume them. So that is how we enforce the transition aspect. There's no lingering references to the previous states, and we've ensured that the state has truly transformed. So this will require some changes to main. We can't assert the content at each stage anymore, but as we've established, we didn't really want to in the first place. So we must also capture each returned post from each of these method calls. But thankfully, we can utilize shadowing, so we don't have to come up with different names each time, which is pretty good. These changes don't really mean we follow the state pattern anymore. The transformations between the states are no longer encapsulated entirely within the post implementation because we're getting back separate types from each method call that exposes that transition typing system. But invalid states are now impossible because we've utilized Rust's type system to enforce our rules of compile time. And this prevents logic bugs from being entered into production and a wide array of other things. So just as a quick summary, we've seen that Rust can implement OO design patterns, but those patterns have trade-offs. Rethinking the problem to take advantage of Rust features can provide benefits, such as preventing logical bugs at compile time. And we now know that you can use trait objects to get some object-oriented features in Rust. Dynamic dispatch can give your code some flexibility in exchange for a bit of runtime performance. And you can use this to implement OO patterns that make your code easier maintained should you wish. An object-oriented pattern won't always be the best solution for a problem with Rust because it won't necessarily take advantage of Rust's strengths. Thank you very much. I realize I've gone quite over time, so apologies, Tim. I can see there's been a lot of chat in the chat. Are there any questions? I realized I did have to blast through that at a pretty rapid pace to fit in the time.
I really appreciate that, Alex. Thank you so much for presenting that. I did kind of had to nip out very quickly for part of it. Did you cover using enums to kind of like unwrap kind of the kind of traits from objects?
No. So that's not covered in this chapter, but also I didn't have time to fit it in either.
Yeah, that's fine.
Sorry about that.
Have you personally looked at it, Alex?
I haven't personally looked at unwrapping enums with it. Right. No, I have used trait objects before to varying degrees of success.
I just want to very quickly kind of share kind of my findings with that, and I would like to be corrected if my findings are inaccurate. But I don't really like using box dynamic because it's like you're allocating and it feels like it's not rustic, in my opinion. So I use enums as a way to kind of package up my types, so it becomes kind of like not like an any in C++, but a variant, right?
Sorry, I told you a lie. So we did touch on this briefly because it's come up in other chapters.
Yeah.
So it's a trade-off, really. If you know, if you can know all of the types that you could possibly use at compile time, then by far that is the better approach.
Yeah.
So the strength of trait objects is when you don't know what your types are going to be at compile time. Say if somebody's extending your library.
So in my example, I was building a game engine, and I used both. I wanted to see what would happen if I used both approaches, and what I found out was that the performance and the decompiled code was exactly the same. So I don't know if in my case, what was happening was it was making assumptions about how to optimize my code away, but from what I could see, there was the way that Rust compiles dynamic boxes and enum, packaged up in enums, seems to be the same. It's certainly the same performance anyway, in my case. But thank you.
It's like with C++, right? The compiler can do the virtualization. So especially if you mark your virtual subclasses as final, right? So the compiler has much more information and it can directly link to the implementation of the class, right? With enums, I personally think it's also like a nicer idea, but it goes against that open close principle. So now if you introduce some state, you would have to change it in all the functions that you would be matching against, right? Enum, basically. And you would have to recompile the code. I think it really matters for larger code bases, whereas with like a state pattern, you would add a state. Potentially, you would have to change the other state, which transitions to that new state, right? But then you would have to like recompile, let's say, 2 files that each implementing the state itself, and you wouldn't have to recompile all the other classes and so on. But like me in general, so state pattern helps. Like really, if your original post, if it had like multiple members, right? But not all the members would be used in every of the state, then the state pattern helps because you can move those members potentially into the state itself. But like in this example, I personally wouldn't see the advantage, right, of using the state pattern, because it helps when implementing, but not necessarily when reading, right? And you don't see really transitions. Like state pattern is nice when you see the UML state diagram, right? But when you read the code, then you don't really see these transitions. You need to read the code of each class and see, oh yeah, this class transitions to this class. Then going through the code, this transitions to this one, right? It's not really necessarily nice. There are libraries like Boost, for instance, in C++, it has some DSL, right, to specify the state and the states and the transition. But it's already like a language on top of the other language. So
yeah, I think that's a big. It kind of leans back into whether OO is the right approach for your problem at hand. So for this example, yeah, you can't see the internals. That is essentially what they're trying to do. Now, if you have a situation where you think your developer wants to understand how the transition works behind the scenes, then clearly you don't want to hide that information away too much. But yeah, I think all of your points there are completely valid, Christoph.
Performance-wise, go ahead.
I was just saying, you just end up having to dock what each of those methods do anyway, in terms of knowing what the next thing was. So you're gonna have to end up exposing the internal details anyway, because you need to get to that second state, but you need to know which method gets you to that second state without knowing what the internal state is.
That's true. I almost wonder if they picked that example deliberately.
Possibly.
Yeah. If I'd had more time, I'd have liked to come up with another example that maybe stressed it a bit more.
So anyway, the design patterns, right? Like as we know them from the Gamma book, Gang 4, they are said to be workarounds around object-oriented programming, right? And hence, that's why in like more functional languages, you don't need those. But those, the functional languages, they have trade-offs of themselves, right? So in fact, there are design patterns in the functional languages to simulate something from the object-oriented world. It's always, there is always a catch.
And as far as performance goes, and I think it's, as usual, you have to like profile it to really know, because I thought I saw something recently on Twitter where dynamic dispatch was actually outperforming static dispatch in one example. So this idea that always switching to static dispatch is better is also, as usual, nothing's always true.
That's true. I should stress that's how the book presents it. And in theory, that it should be faster. Now, why in that particular example it's not? It's got to be down to some weird optimization, virtualization stuff, right? But in the theory, with no additional extras from your compiler, then yeah, it should be better as static. But
similarly, I remember Richard was presenting some work on comparing code on C++ and Rust using enums in Rust and variants in C++. And as the result, it came out that the C++ was slower. And I had a look at the code. I just don't remember what the outcome was. But I remember, for instance, compiling the same code, not on MSVC, but on Clang or GCC, was having the same performance outcome as the Rust. So it was only MSVC that made it slower, right? So yeah, if you really worry about the performance, you do have to benchmark it.
Yeah. Otherwise, it's all just crystal ball stuff.
So we are kind of overrunning. We've had some really great chat, so I really appreciate that. Tim, do we still want to do chapter 18, or do you need to kind of leave it until next time? Are you happy to carry on?
I'm happy either way. I'm not offended if we want to quit. I mean, it's been almost an hour, so I'm happy to go either way, whichever you want to do.
Okay. Well, I think we're all here, so shall we carry on? Yeah. General nods. Okay. Cool. All right. Let's carry on.
You're gonna need to stop sharing, Alex.
Oh yes, of course.
Also exciting because it's going from like a non-traditional Rust pattern into like some very Rust code of pattern matching.
Sorry for stealing all your time, Tim.
So thank you very much again, Tim, for running through chapter 18 with us. It's greatly appreciated. It. Thank you.
Sure. Where's my slides? What happened?
Maybe Notepad.
What happened? No, what?
Did they?
I must have closed the Firefox entirely. Sorry, I had them all queued up. And
No, it's fine. Also, if you'd rather leave it, it's obviously totally up to you. We're all little kiddos wanting more content.
Well, it's only like 2:30 in the afternoon here, but I mean it's getting late over there. Where am I going? I just posted these. Should be the first one. All right. Is that it? All right. So, chapter 18 is patterns and matching. The book divides it into 3 sections: all the places pattern can be used, refutability, whether a pattern might be able to match, and pattern syntax. And I've added a sort of review section at the beginning. So, because we already saw some pattern matching back in chapter 6, so some of this we can sort of look at again. And I think to a lot of us, pattern matching seems kind of weird. But if you've done any functional programming in F# or OCaml or something, then this will seem pretty familiar. So a lot of people find this weird and have to go over it a number of times. But if you've used any of these other languages, it's kind of like that. It's pretty much the same thing as OCaml or any of these ML-based things. So we had this coin example because chapter 6 was on enums, and we just talked about matching in the context of enums. So if we have this C-style enum, then we can just match it. And the important property here is that it has to be exhaustive. We have to account for every variant of the enum. If we added a $50 into the enum, then this code would stop compiling until we added the $50 back into the match. And then the more Rust-like enum that has a data in one of the variants, or more to the point, not all the variants are the same, then what happens? Then when we can match and also destructure the data out of the variant that has it, and do whatever we want. So this coin thing is being matched against a quarter, and we're sort of declaring a local variable here that has the data that was in our coin, and then we can use it here. And in case you were wondering what that's all about, the US coins, this is what quarters look like for years. And then 20 or so years ago, they started making state quarters where the heads were the same on all of them, but the tails were different by state. So here's the North Dakota with a couple of bison. I don't know if you can make that out. And they I think were 5 every year for 10 years until they had all 50 states represented. So that's what that's all about. If you were wondering what the example in the book was, what these state quarters were all about. It occurs to me, we still have regular quarters, so they probably should have made this an option of a state, because you might not get a state. So moreover, they don't mention this at all, but when all 50 states were done, then the next year they issued some territories like Puerto Rico and Guam and whatnot that are not states technically, but they got their state quarters. So maybe you should have another category. Furthermore, then the US Mint was drunk with power, I guess. They didn't go back to the regular quarter still. They had national parks and whatnot. And they've just stopped doing that. They're still not going back to the regular quarters this year. Prominent US women are going to be featured on the tails of quarters. So we have all these. Oh, also, this isn't the first time. Back in the 70s, we had a bicentennial quarter, which again, the heads were pretty much the same. The tails were different. So maybe if we were thinking about modeling pocket change, we could use the type system and do it a lot better, but we would sort of need enums of enums and whatnot. So I think it's useful to think about really modeling real data. And I don't know this is kind of I used to think this was a good example for Americans, but bad for a book with international desires or whatever. But now, after thinking about it, going through these slides, it's like, I'm not even sure I like this example just as data modeling or whatever. So I like to think of a better example with more international appeal for, maybe I'll put a pull request on the book or something. But anyway, also in chapter 6, we looked at perhaps the most famous Enum, and that's the option type. And we can match on that as well. And then also in chapter 6, we looked at this sort of alternative syntax for if-let, which this function does exactly the same thing as this one. Just instead of match, we're using this if-let notation. But it does the same thing. All right, first section of chapter 18 talks about all the places that patterns can be used. And the first is match arms, which is just what we were just looking at. And then the if-let. And it's maybe worth pointing out that if-let is not exhaustive like match, but you can still put an else on there like a regular if. So you can sort of do match your pattern or not match your pattern at least. And then there's a while-let, which works similarly. When the match fails, the loop ends. So same idea. Also, for loops take a pattern. So you might think of that as just your variable for your loop, but it in fact is a pattern. So if our iterator enumerates, then we're going to get a pair instead of just, if we iterate through this vector, we'll get A, B, and C. But if we enumerate that vector, we're going to get 0A, 1B, and 2C. Well, we can destructure that right in place in the for loop and get out the individual values. So for loops are pattern matching too. And then perhaps the most surprising, especially for people who haven't looked at any functional languages, is let binding is really pattern matching. We think of it as simple variable assignment, but it's pattern matching. This first let statement is how we usually think of it. We can assign a tuple to a variable, but we can also destructure a tuple, but with a let binding, just and we'll get out our individual x's and y's and z's that way. So I know the first time I looked at something like this, it was, I think, in Elixir. And I thought Elixir was really strange for reasons like this, but now I'm sort of used to it. But I imagine that people learning Rust are not comfortable with this. And even though it's a simpler example than the match statement, it just seems weirder philosophically somehow to me. And of course, this is an error if it doesn't match. If we try and destructure a tuple and we don't have enough places to put the things, then this is an error. And of course, that's in Rust, it's a compile time error. So we could stick an underscore in so the match succeeds, but we don't care about the third thing. So we don't match it to anything or don't bind it to anything. And then that will work. And the next example is function parameters. They also take patterns. Again, we think of these as just names of variables, but we can do pattern matching right in the function name. So here's an example where this function takes a reference to a pair of integers, but we're destructuring the reference and the pair right in place and accessing the two integers. And of course, closures work exactly the same as functions for exactly the same reasons. As of just a few days ago, we can even destructure in simple assignments. So, I thought, if you think it's weird that let binding is actually pattern matching, then you can even do it without the let binding. It's like, this is just destructuring sort of simple assignment So if you haven't upgraded to 159 yet, then this won't work. But I think this came out exactly a week ago. All right, the next section, refutability, whether a pattern might match or not, or might fail or not. So there's two kinds, irrefutable and refutable, and we sort of looked at both already. Sort of the one difference between let binding and if let is let has to be irrefutable. This can't fail, whereas if let is the match might fail, and if it does, that's the sort of not true case, not branch. So the function parameters and the for loops, as well as the let statements, require irrefutable matching. If let and while let are meant to be refutable, but if we improperly use a refutable pattern, it's an error. We can't, and it's a type error, of course. If we try and say just let some x equal y, well, y is presumably an option, and it might be some value, but it might be none, and that's not. This won't compile because the none case is not taken care of here, like it would be with an exhaustive match. Improperly using an irrefutable pattern is a warning, because this will compile and run, but it's kind of dumb. So the compiler sort of just wants you to know that this is dumb. Maybe it's not what you meant. And then the match that we were first looking at, each arm of the match is refutable except for the last one, which is supposed to account for everything else. So it sort of has to be irrefutable. And now pattern syntax. We might have actually seen all of this by now, but we'll sort of go through it. So the simple match with an actual literal match. And this is the example right out of the book for what they call matching named variables. What they're getting at here is that this y has nothing to do with this y. We're matching on x, which is sum 5. So we look at sum 5 does not match sum 50. We go on to the next one. Sum 5 does match sum y and binds y to 5. So this will print out y equals 5. And then here, that shadow of binding to y goes away. So this will print out y is 10 again. So that's what that example was getting at. And then we use pipe for or, so we can match 1 or 2 with this syntax here. And we can match a range with the usual sort of range syntax. So we don't have to type 1 or 2 or 3 or 4 or 5. We can type 1 to 5 in a range. And we can also do that with characters. So, which isn't too surprising, I guess, if you think about it. Characters are sort of just U32s. But that's it. Numeric, what is there, 17 kinds of numbers, and then characters. That's all you can use the range with. Destructuring. We can destructure all these things in pattern matching. And we sort of already looked at this, I think. We sort of assign a point with the structure on the right. Well, we can sort of destructure a point with this on the left. We say we'll take the x thing and store it in a variable. We'll take the y thing and store it in a b variable and print it out. Or we're going to get the 0 and the 7 that way. There's this shorthand where if we name the x thing x and the y thing y, then we don't have to write x colon x. We can just write x. So this does the same thing with the shorthand notation, which is quite common and idiomatic. You'll see that in a lot of code if you read other people's code. So destructuring enums, if we have an enum like this, where we have this sort of struct-like data, this sort of scalar data, and this sort of tuple-like data, then we can And if we have a message that matches one of them, then we can destructure it with a match statement like this. And here's that sort of shorthand matching for the struct like, and here's where we're matching the tuple like, which would actually match in our example, because that's the one that matches, right? Yeah. Did I miss something? No, that's what we just said. I went backwards instead of forwards or something. So in my sort of more complicated pocket change model, if we still wanted to print out the state quarter and ignore all those other variants, we could destructure sort of two levels at once. So that deeper model, there's different kinds of quarters, and then quarters are also in Enum. So this will match on quarters that are in the US state series, and then destructure the state into the state variable and print it out. And then we need this other variant, which will ignore all the other kinds of quarters, or match all the other kinds of quarters. We don't care what series they're in, we're just going to return the 25. And you might do something different in practice, but this is just to show that you can sort of match two levels or more deep of structs and enums of structs and so forth. Destructuring tuples, I guess we've already seen several times. Destructuring references, we sort of saw in one of the functional examples or whatever, but here it is a plain old let binding. And again, this might not be what you do, but it's perfectly valid, right? You're more likely write this, and that's why we think of sort of let binding as sort of just being a variable declaration. But you could also pattern match a reference and get the value out that way. And lastly, we have ignoring values in patterns. So we've already looked at ignoring the entire value with an underscore. So here's a function that takes two variables, and we're just ignoring the first one. Well, I don't know why you would do that in practice, but maybe you would. Just something I'm not thinking of. And then a sort of nested match, we can ignore parts of the match. So here, this insists on this being a 1. The second thing can be anything, and we're going to bind it to y. And the third thing we're just going to ignore. And then we can get rid of the unused warning by naming a variable starting with underscore. So this program would give us a warning for y, but not for underscore x. But it still binds the variable. So this code won't compile, because even though we don't care about underscore s, it still moves s, right? This is an optional string. It's going to move that into there, and then it's not a variable, not available anymore when we get to here. Whereas plain old underscore works fine, so that doesn't do the move. So it's not exactly equivalent that underscore and underscore identifier are the same, are always the same. There's this move semantics issue still. So people that like to always put, underscore x instead of just underscore to ignore something, you can get bit by that sometimes if there's moves involved. And then there's this sort of yada yada operator where you can bind x to the first thing and just sort of ignore yada yada yada, ignore everything else. I don't know if this is pronounced, I don't know if dot dot is pronounced yada yada in Rust, but it is in some other languages. And then there's match guards, where we have sort of this suffix if notation, where we're going to match some 4 only if it's less than 5. And then we still have to sort of account for all the other x's, so we still need another sum x without. And I think we need to put that without, like, I don't think it's okay to put some x if x is greater than or equal to 5. Rust doesn't check the sort of match guards as part of their exhaustive check or whatever. So this wouldn't count as exhaustive until we sort of have an underscore or this guy without any conditions on it to sort of take the rest of the cases into account. Lastly, we have at bindings. So if we have this enum with just one ID thing in it, then this will print found an ID in 5. So here we're matching on the ID in this range, 3 to 7 inclusive. And normally, like in this case, this matches 10 to 12 inclusive, but we don't know which it was. It could be 10 or 11 or 12, and we have no access to what the data was. This is going to bind whatever the value that matched was to ID value, and then we can print out the actual 5. And you might say, but this guy binds the value. So what happened? Right? Why does this guy get the value and this guy doesn't without this at notation? Well, it's exactly because of the extra condition. If you look at the second case, there's nothing. Right? The guy that's missing here. Let's go to the next slide. I think, yeah. So it's that shorthand notation we talked about earlier. And Rust Analyzer is helping us out here. The ID that's missing isn't the white one. It's the cyan one, right? It's the tag that we don't have to write in the shorthand notation, not the binding name or whatever. So if you do want to match and also bind the value, then you sort of need this extra at notation to do both. And some other things you might want to look at. So that's the end of chapter 18. There's more things to look at in the Rust reference. Where preparing these slides, I couldn't decide if I wanted to use value or expression for these pattern matching things. The terminology used in the reference is scrutiny. So you pattern match on a scrutiny, which could be a value or an expression. And they go on to say what happens if it's an expression. It evaluates it once and stores the result somewhere and uses that as a value, temporary value for all the legs of the match and so on. As you can guess, fairly complicated. And then there's a separate page in the Rust reference for patterns. And then in Rust by example, there's 3 separate pages, one for match, one for if let, and one for while let. And that's all I had.
That was great. I love pattern matching.
Thank you so much, Tim. That was fantastic.
You're welcome. I'm glad you liked it.
Kind of syntax, yeah.
Do we have any questions? Sorry.
I'm sorry, what?
Did we have any questions for Tim? Any more questions?
Christoph was just trying to say about what C++ is doing, I think.
Sorry.
Trying to not share my screen. How do I not? Stop share. Maybe that'll do it. Here we go. Oh, now I can look at the chat.
Yeah, it should be coming in C++. Yeah, I think.
There are proposals, but probably it's going to be like C++ 32 or something.
I think, what was it? I think Herb said something about 23, and then later on in the conference, somebody else said that's not going to happen. So
23 seems alarmingly soon now, right? If you're the one trying to implement this.
Yeah.
It might be that it's already like all the proposals that come into 2023, they're already chosen, right? Like nothing else. Yeah, I think so. So it's already closed for new proposals.
Well, if you grab the experimental circle compiler, you can try it today. Which I think Kira, you spoke about that a few months ago, didn't you?
Yeah, it can't do everything, but it definitely gives you a flavor of of what it's going to be like in the context of C++, which is nice. Yeah, I really like this the named struct parts of the pattern matching as well. I think it's just really, really nice. It's just lots of places, lots of boilerplate code that you just lose. You don't have to faff around with. You can be really nice and type safe, and without having to be like, oh, and now I need to unpack everything inside the struct. Yeah.
Quite not up to date with the number 23, into which it's a reference.
Oh, the C++ 23.
Oh, okay.
Sorry, yeah.
Gotcha.
It's just the next, the
Sure.
next big one.
For me with the pattern matching, it is nice. Like initially, if I remember correctly, I was beaten by the match guards, and when you're matching, you need to match against constants, I think, or compile time evaluable things. You cannot just say, oh, I'm gonna pass in a variable into the function, and then the guard will be using that variable, I think. So it needs to be the branching strategy needs to be known at the compile time, I think, which was something that I wished was different originally, but it is what it is, right?
I guess that's what makes it different that's what makes it a match rather than just an if. Is if you want it to be fully flexible, then yeah, you can just have conditional branching. But if you want to be able to take advantage of what you do know about it, then match really shines. But I know what you mean, though. I also initially was like, I just want it to do everything. I don't want to have to use anything else now. I've gotten comfortable. I actually have to shoot on, but you guys keep chatting. I'll see you all later.
Later.
Thank you very much, guys. Thank
I will
you.
have to go as well. Thank you, Alex. Thank you, team. Really good presentation, as always.